Thank you. Thank you very much. And thank you, Professor Tajima, for including me in this, informative and productive forum. So, I'm going to start by following on sort of what Katie just talked about, from these perspectives. How do we envision, how do we reach the solutions? Okay, so let me bring up my presentation. Now, before I start, I had, worked in the national labs on, amazingly, it was 20 some years ago, started on nuclear waste transmutation solutions. And then going on to Generation 4 nuclear energy system, advanced fuel cycle initiative and stuff. So by very fortunate circumstances, I was able to get into this sort of early renewal of the civilian nuclear energy in the United States and then around the world. And then by before 2008 or 2009, another set of fortunate circumstances set in. Bill Gates of the Microsoft fame, and collected people started to thinking about energy solutions to the climate problem. And I was very fortunate to be part of that. And so during that process, I was sort of stepping gradually away from the scientist approach of sort of observe and study, not interfere, to a more of engineering technologies, sort of a mode of actually trying to come up with solutions. And so this is my sort of a presentation of nearly 3 decades of work on nuclear energy. And also in the interim time, I also had the opportunity to work with many amazing entrepreneur investors in other part of the clean energy, like renewable energies and also energy storage, electric vehicle, etc. So here's a sort of we are switching gear a little bit toward the solution part of this session. Now, because once I started working with the developers, the entrepreneurs, investors, and looking at all these problems, time become immediate, obvious constraint on what we can do. Okay, so I don't need to go through the gigantic scope of the climate change of global energy and also the opportunities it generates. But in this sort of a big picture, sort of a frame, where is nuclear energy? What can nuclear energy, do in a realistic time scale that really affects? Okay, if anything, today's preceding talks just only added to my urgency of this. I've heard people, talk about the permafrost melting and releasing of methane, and then the ice sheet melting. These only have not like 3 decades or 4 decades of time response time, just only a few years to 15 years of time. But having worked in the nuclear for such a long time and across many fields and applications, it started with a bang, I would say. In the 1950s and 60s, Atom for Peace, nuclear energy will become too cheap to meter, etc. And then 3 very catastrophic accidents happened: the 3 Mile Island, Chernobyl, and Fukushima, that really stopped the further growth and expansion of nuclear power. And so by 1996, the global share of nuclear electricity peaked at about 17.6%, and now it's dropped down to about 10%. So, as a practitioner myself, I've been dreaming for nuclear renaissance for 20-some years, and we are still kind of dreaming, although there are some signs of renewed development that's coming out in recent years, but we are far from getting there. Okay, I saw in the chat room that people were asking about the China's nuclear power development. Even that was the largest civilian nuclear program in the world and the fastest growing market. it still pales in comparison to other forms of clean energy and energy storage. I won't need to talk about fusion because, you know, we will have a dedicated discussion on this, but fusion was also sort of a, you know, people jokingly say fusion energy is always 30 years away. Okay, so how do we approach this? So one of the things that because I've had to step out of just study, you know, observation and study and do lots of development and investment. So I started thinking, you know, do we continue to do more of the same? Or maybe we should think different. Okay, you know, here's one of my favorite quotes of Einstein's, is we cannot solve our problems with the same level of thinking that created them. Okay? Like Kate said, lots of the problem that we developed was because we know how to deal with fossil fuels, deal with all these things, and our humans sort of a, you know, innate urge just to do more created bigger and bigger problem as we do more and more of these things. So maybe it's time, you know, given the state of all these accumulated knowledge and skills and capacities and advances, can we, you know, think them from a fundamental and systematic point of view and rethink the problem and rethink the solution. So my approach present here is to organize the solution thinking through the understanding of the primary energy hierarchies and achieve fundamental nuclear safety by the whole system engineering design, and taking into account the major system and cycles on Earth. If we, you know, the climate change was a major imbalance because we did something to the system and cycles since the Industrial Revolution. So if we're going to solve that problem, reverse the trend, we have to start thinking at that level. So, you know, this is sort of my key sort of insights and finding for this, and sort of a preview of the later part of my presentation. One is nuclear energy is truly unique from the primary energy hierarchy sort of a perspective. It is not part of the sort of our biologically relevant material cycles on Earth. Okay, all the nuclear elements, etc., exist kind of outside the biosphere and cycles that's biologically relevant. Okay? And then the other is artificial nuclear fission. It's also different from most other energy systems in that it's self-sustained and not driven system. Most of energy systems are driven in the sense of you add fuel, you stoke fire, or in the case of fusion, you drive with plasma confinement or injection of something. Nuclear and artificial nuclear energy, or what I call artificial nuclear fission, is self-sustained, it's not driven. Once you get started, you can't stop it. So the fundamental safety with sort of a new safety category and design principles can be achieved from robust fuel, meltdown-proof reactors, and differentiated design, which I will expand. So let's start with the sort of the primary energy hierarchy. Okay, so this is what a physicist view of the origins and transformation of all the primary energy on Earth. And we have the majority of it, over 90% of it, is nuclear origin. And of course, most of it is from the solar sun's fusion that comes cascade down to all the biomass, fossil fuel, thermal and photovoltaic, etc. And then coupled with a little few percentage contribution from the gravity, mostly the Earth's moon, we have some sort of a hydro, wind, and tidal portion of it. And the fission part, we've always kind of had the geothermal part, which is a part of the fission sort of thing on Earth. But what I call artificial fission, which is the traditional nuclear power, is what we are able to apply the science and technology and generate energy. Now, in this hierarchies, from the top and down, every time it goes down a level, the energy is drastically diluted. Okay, the density, the flux and stuff is diluted. And then it goes back up and concentrates. So the only thing that in the Earth, in the natural sort of form of primary energy, fossil fuel is naturally concentrated for us by the geothermal and chemical process. And this is the qualitative picture. Now, if we look at it more quantitatively, and I want to distill everything down to the most fundamental interactions forces, I'm using the electron volts of each unit, whether it's atom, nucleus, atom, or molecules, when they, what the energy barrier you have to overcome, and then what's the energy release, and what would be the thermal energy, whether the temperature it's working at, or the output is the system is operating at. So, on this scale, which is only, on the milli-electron volts to tens of electron volts, you can see fire is much higher than wind and hydro. Okay? And we got helped by nature because of the lightning, striking of stones, etc. Then we were able to use fire as our primary energy before the Industrial Revolution. And then we discovered the use of fossil energy. The fossil energy, look at the scale, on the vertical scale, now it's 100 times more than the previous one. And on this scale, chemical energy dominates, and those fire, wind, and hydro just sort of disappeared on the scale. And of course, we also had the solar energy, which is the largest growing energy in the last decade or so. It will be, from this year on, I think it's going to be the dominant new capacities of energy generation globally. And we also helped by the nature, because we're able to use fire and naturally existent sort of reactions preceding this sort of a seemingly more difficult form of energy. And then you move forward a little bit, you look at nuclear. Now I have to increase the scale, the vertical scale, by 6, 7, 8 order of magnitude. And then all these things just disappear. Okay? This is dominated by nuclear fission and nuclear fusion. Okay? So that shows that, that the potential what nuclear can do, if we do use the energy from nuclear fission and nuclear fusion. Now, I have to sort of use a logarithmic scale now to put everything together in one picture that you can see. Okay? And you can see the progression of the difficulties of using them, and also the potential of using them. Okay, and now in the case of nuclear fission, we were also helped by the nature that the nuclear synthesis that happened in the cosmos that gave us a lot of the neutrons that are not stable. So you can actually make nuclear fissions self-initiated, self-sustaining as compared to nuclear fusion. And the difficulty, of course, and not just the difficulty, the reality is we cannot exceed currently, for the foreseeable future, the bond strengths of materials is in this band. Okay, so we have to know what our constraints are, and this is the constraint that we cannot escape from. But you can see nuclear, with the barrier we can overcome, the energy is so large, but the working condition is possible under this. Okay, now fission is very different. Fission have to solve a whole different set of problems. Fusion. So we've all had this sort of urgency discussion before, and here is again using that energy sort of a thing. Look at just biological life, sort of metabolism and lifespan. Okay, they are sort of determined by the Arrhenius equations through this activation energy. And 2-degree increase of average temperature on the surface of the Earth would increase the metabolism by about 20% and will shorten the lifespan by 20 to 30%. This is sort of a drastic change that biological evolution just cannot adapt to. And this is not just sort of happening on sort of these particular thing. If you look at, one of my sort of favorite physicists in a book about, how the social and city development that's happening, they are all accelerating at sort of a super exponential scale. So we are basically having a compounding problem, and the problem coming at us is bigger and faster. So how do we apply this sort of a thinking and the constraint to our nuclear problem? So now understanding the primary energy hierarchy and having sort of a view of the cycles, we now understand the artificial nuclear energy can only be utilized through heat. Okay? And it's not a driven system. Okay? They are not driven. We need to control them at criticality. And this is different from any other system, which will change to a wholesale changes in the safety categories, in the design principles, and how we build and operate the systems. So by fundamental safety, I'm talking about the typical reactor safety, but also expanded to include ecological, environmental safety, economic, regulatory, investment safety, and non-proliferation nuclear material safety. And this will lead to a set of things we need to be doing. Okay. Now, it looks like a daunting challenge that how do you do all this stuff and in the short amount of time that's available? Well, if we go back again to the basics, we may be able to have an understanding how we can do these things, and then without bringing or minimize unintended or unknown consequences. Okay, one of the things is if you look at the major systems and materials, all the previous 6 presentations in some ways talk about the systems we are in and the cycles, whether it's carbon, oxygen, water, nitrogen, phosphorus. And these cycles, if they are driven by external energy, can be sustainable. It has been sustainable on Earth for billions of years. Okay? And also because we are part of the system, using that system to generate energy is the most familiar approach to us. So we do a lot of it. And that got us into the trouble. So one is we are able to scale them up very quickly. And of course, once we scale them very quickly, we also cause us all these problems. And these problems are inherent in all these fossil fuels, but also in many of the renewable energy systems that are in them. They embedded in because we are changing the system and cycles. The nuclear materials energy, however, is managed from the beginning to the end, and that's separate. The material and energy is separate from the biological system. Okay, but this also gives us the severe disadvantage because unlike the fossil fuels energy, lots of people know and how to do it. You look at that coal presentations picture, these things are miles and miles big, open pit mining and all these things because people know how to do them. Nuclear is limited in that perspective. So the advantage of it, not in the major cycles and systems, is also a disadvantage of doing them. So we have to somehow bring in this use of nuclear energy sort of through some accelerated approach that minimizes this barrier. Okay? Now, one of the barriers is how we think about nuclear energy. For over 6-7 decades, we thought, based on the early understanding and presumptions, is the fissile elements were very rare. We need a fast reactor with high breeding ratio to meet growing energy needs. But the MIT study for the future of nuclear fuel cycle in 2011 pointed out these assumptions are outdated and mistaken. Okay? And so, if we are working on outdated and mistaken assumptions, presumptions, the more we do, the more trouble we got into. and we just can't move it, as evidenced by nearly 3 decades of stagnation or decline of global nuclear energy. So you look at, these assumptions, what I call a cosmic sort of energy cycle, is thorium and uranium, uranium is a predominant fissile material for nuclear power, is really, really abundant. Okay? We have 40 trillion tons of uranium in Earth's crust, 4 billion tons in seawater, which is kept in equilibrium with the rocks. And then we only use 8 to 9 million tons per year, globally right now. And the price per energy output is less than 1/100th of the price of natural gas, okay? So, we were designing an operating system based on sort of a totally different reality of the availability and the cost of these resources. So
5 minutes more.
Yeah, okay. So the increasing safety requirements led to degrading economies and the flexibility of deployment that lead to the lack of fundamental economic, regulatory, investment safety. And the current technologies often added the complexity and cost, so making it lack of fundamental assets, evolution in ecological, environmental, and regulatory safety. Okay, mainstream reactor designs, while they were adapted from the early military uses, so they lack of the fundamental non-proliferation nuclear materials. So on the one hand, we want to do more clean energy, low carbon energy, but on the other hand, we have many headwinds that are opposing its growth and expansion. And so, in one picture, I can show that because of how we approach to the design of construction and operation of the system, is we added layers and layers of safety emergency system without fundamentally eliminating sort of the problem of nuclear power. And the tracing the source is the power density of the fuels too high, the radioactivity leakage barriers are not high enough. And the reactor design have too much power and too high a power density. And not only they are only suitable for large baseload powering large grids, you can hardly build them in less than a decade or two's time. Okay, so you cannot do much about nuclear energy, and so this is why it's sort of a lagging behind. So, you step back with the understanding of the uranium resources, and then ask, why do we use nuclear power? Okay, we use electricity, use heat, use propulsion, and of course, it obviously needs to be the ease and safety of ownership and investment, etc. And now, in this context, we are also talking about mitigate climate change, and we have to scale up the deployment in time. Otherwise, it becomes sort of a, less of a contributor. So, I don't have the time to go into how these things were derived, because we are also developing and investing in these. So this is what's built from the ground up. And we sort of reached the sort of a more abstract level, these main points. The one is we need the robust fuel and the meltdown-proof reactors, and also differentiated design. Okay? And so the safety-based design principles have to be rethought, because nuclear energy systems are so different from the other. I saw an earlier presentation about effective power density of nuclear, which is actually lower than natural gas by his calculation. It's still the missing element that's considered there is nuclear power density, although it looks low, the energy density is 100,000 times higher, 10,000 to 100,000 times. So when nuclear reactor stops, it's not a stopped system, it's still an energy system. So we have to reconsider how we design the systems by considering the shutdown conditions and then the operating conditions. Okay, then pick the level that's suitable to use. Okay? So that will lead to a very different change of kind of nuclear reactor. And then we can redefine the safety levels from the fundamental safety, which is no fuel damage, no reactivity leak, to sort of a radioactivity safety. Okay? Reactor can be damaged, but fuel is not damaged. To the probabilistic safety, which is what the currently adapted. Okay? There's a small probability of those things happening. And that sort of give us sort of in a schematic way that how we should, instead of making the reactor more compact, higher energy and total power, we should relax so that the other consequences are reduced. Okay, so there's an optimization that's going on with this approach. And the differentiated sort of design. You look at these, what I show here in the pictures, is all these similar technologies for different purposes. You design them differently, and sometimes with the opposite design objectives. But the nuclear reactor was, the main nuclear reactors were a sort of a more direct adaptation from the early military uses, and we've never really veered far from it. And so new nuclear would have to be somewhat different from it. Okay? So to summarize, I think the nuclear energy suffers from these challenges: rising costs, safety concerns, and very limited markets. And the convention problems typically creates cost and safety dilemma. And of course, there's also the safety, security, and non-proliferation. And those are post-design add-ons. So they always add to the complexity and cost. And I proposed, and we are in practice doing these, is to rethink the safety goal and design principles, and then basically get into the nuclear 2.0 fundamentally safe and manufactured system. I will conclude here just sort of recalling a conversation I had when I was advising Bill Gates, and we had sit down talks with the leading nuclear executives, and he kind of half jokingly saying, I don't understand the Gen 3, Gen 4 nuclear energies. It's making the same output. It's just more costly and more more layers of system. How do you survive in a technological world, which, well, it wouldn't? Okay, so there's something fundamentally that can be improved and needed for the civilian nuclear energy. And here's a way that we proposed how to approach. So with that, I will, and also this thing on the left here, Doomed to Cooperate, is written, edited by my mentor and good friend, Dr. Siegfried Hecker, who is probably quite well known in Russia. And this is a picture of Dr. Hecker shaking hands with the father of the Soviet atomic bomb. And the title of the Doomed to Cooperate is also very relevant for our today's discussion with the climate change that we are doomed to cooperate. Thank you very much.